All right, today we're doing 1.5, day 2. So we're applying equations, but we're using motion problems. All right, so um, our objectives then today are to solve problems involving the distance formula, D equals RT. Okay, that's going to be our focus. I want you to remember these problem solving tips. Okay, we've done some problem solving uh, well, ever since you've been here. But remember these steps to help you out, right? You want to read the problem carefully, okay, so that you can note any important words, key phrases, the type of problem, any unknown quantities that you could represent algebraically. Okay, then you have to plan, okay, which means to organize the information so that it can actually be helpful to you. So it takes some time to do the problem solving, but that's what this whole like 1.5 is. Solve, we're going to write an equation. Okay, this is Algebra 2. You should be writing equations to solve these things. I'm going to give you a template to really help you understand the problem solving here. But writing an equation with them and then check. Okay, relate the solution to the problem and answer like all the questions. Like make sure you answer all the questions and then make sure it's reasonable. Like ask yourself, is this reasonable? All right. Then you'll see that I have left those helpful equation writing tips there. They're not going to be as helpful probably for this section, but they are there. Then we're going to look at some motion problems. These are problems that lots of people really kind of despise. Sorry, I've got to move my paper over there. Got a little wonky. All right, so motion problems. We're going to be using the basic formula of rate times time equals distance. This is what we're working on today. Can help you organize information in motion problems. So if we look at these things, it may not make sense yet, but hopefully it will in a second. Okay, if we are looking at a round trip or a pursuit problem, okay, so if you go to school and you come back, okay, this is what happens. Your distance here, like your first distance, say you're going to school, is the same as your second distance, which is coming home. This is why this one is a round trip. Okay, so these are like your starting and ending points. Okay, it's also a pursuit problem. So if I leave and go to school first, and then, well, let's see. That's a good, I was like trying to think of a better example that you guys could relate to. But if I leave and maybe go to church, because my husband and I go to the same place. If I leave and go to church because I have to be there early to help do something on Sunday morning, then I leave and go to church, and then my husband leaves the house and 30 minutes later and comes to church. That's a pursuit problem, but we've traveled the same distance. We left from the same place and we went to the same place. So they're a pursuit problem. So in this case, distance 1 is equal to distance 2. Okay, and we can solve it like that, or it's going to help us think about it. The next type of problem, though, is motion in opposite directions. Okay, these are opposite direction problems. All right. So, in this case, we have a total distance. Okay, this is in. In is our total distance overall. But the deal is when we're traveling in opposite directions, one of us is starting here on the left side, and one of us is starting on the right side, and we're meeting in the middle. And how we find that total distance is we add distance 1 and distance 2 together to get the total, the new total. And it works the other way too. If we're both starting at the same place and one of us is going one direction and one is going the opposite direction, it's still, if we add those distances together, D1 and D2, we still get that total, that new total distance. So we can either start at different places and meet in the middle, or we can start at the same point and go different distances to get this opposite direction. All right. And the last one. Okay, the last one is different distances. Okay, so if we're traveling different distances. So here's the deal. If Okay, so again, if I'm talking about my husband and I going to work, um, excuse me, because he works a little farther from our home than I do. Okay, so he works at United Rentals. So if my husband would leave and go to work, um, and then I left 10 minutes later, okay, but I got to work at the same time as he did or something. Okay, we have traveled different distances. So there's this amount, because I work a shorter amount, that I have to include in there. So I would have to say, like I work 5 miles closer to home. So this would be 5 plus the distance I drive equals the distance that my husband drives. So now there's some new amount in this problem because of the different distances. And it doesn't matter where you put the extra distance, okay? It could also be an example of running, okay, or something. So we could say John ran 17 miles long or farther than Julie. Okay, so here's Julie. John was 17. We don't know what Julie is, but we know that he ran 17 miles farther. So that would be this number, how much further he ran. Okay, so these are different distances. So sometimes just figuring out which ones are which is helpful. Okay, putting in some information and figuring out which ones are which. Okay, so Ted and Jeff, let's look at example 2. Ted and Jeff planned to leave the church at 9 a.m. to go camping, but Jeff was delayed until 9:30 a.m. By driving an average of 8 miles per hour faster than Ted, Jeff arrived at the campground at noon, the same time as Ted. What was the average rate of speed for both Ted and Jeff? So first of all, what kind of problem is this? Is it a pursuit or round trip? Is it opposite directions? Is it different distances? That's what I'm going to go with first. All right, it's pursuit. Great. So this is a pursuit problem. So I'm going to switch to red, which means that it's equal distances. All right, perfect. Now, this table is here to help us. It's rate times time equals distance. And so the table is here to help us. All right, we're going to put in the information that we know. So first we know we have Ted and Jeff. So I'm just going to put T for Ted, J for Jeff. Okay, they leave the church. They plan to leave the church at 9 a.m. to go camping, but Jeff was delayed until 9:30. Okay, so Jeff delayed until 9:30. Okay, and Ted left at 9 then. So this is Ted. By driving an average of 8 miles per hour faster than Ted, Jeff arrived at the campground at noon, the same time as Ted. So they arrived at noon, the same time as Ted. What was the average rate of speed for both Ted and Jeff? So we've got to find that. All right, but here's the thing that we can think about. So in the formula, rate, time, and distance, and the formula is rate times time equals distance. Okay, so in this formula, we have to know the rate. Well, the only thing we know about the rate is that driving an average of 8 miles faster than Ted. So we know Jeff drove 8 miles faster than Ted, but we don't know how fast Ted drove. So in our rate, we could say, all right, well, we don't know how fast Ted drove, but we do know Jeff was Ted's speed. He drove as fast as Ted plus 8 miles per hour faster. So he's going to be T plus 8. Okay, and then the time. Okay, the time is not the time that they arrived, right? It's how long, it's the duration of how long they drove. So we're going to have to do some math to figure that out. Okay, because this is not the time of arrival, this is duration. Okay, you may want to put a note there that time means duration, amount of time. Okay. All right, so we're going to have to do some math on that. So we know Ted, right? They've left at 9 a.m. Okay, so Ted was on the road from 9 a.m. and he arrived at the campground at noon. Okay, so if he drove from 9 to noon, how long did he drive for? Well, that's 3 hours. Okay, so over here for Ted, we're going to put our time as 3 hours. Then Jeff, right? Jeff was delayed until 9:30, but he also arrived at noon. So instead of being on the road for 3 hours, he was only there for 2.5. Perfect. Okay, now the cool thing about this chart right now, how the chart is helpful, is that this, again, rate times time equals the distance. So to fill in this column of distance, we're going to use this formula here. So we're going to take times time, or t, sorry, for Ted's rate times 3. So this is going to be 3t. So I just multiplied these together to get the number that goes right there. And then I'm going to do the same thing here. But remember, this is a quantity. So we're going to do 2.5 times t plus 8. It has to be distributed. So this is going to equal 2.5t plus, and you wouldn't have to write it out there. You could leave it plus 20. You could also leave it as 2.5 times t plus 8 for now, if you wanted to. Because, all right, now that we've got all of our information sorted, we're going to take this information. So we're going to take this information right here, okay, and we're going to put it into an equation like this, because it's a round trip pursuit equation. That's what we decided. It was a pursuit equation. So we're going to set those distances, these distances, we're going to set them equal and solve. Okay, so we've got, let me erase this little bit of work here. So we've got 3t equals 2.5t plus 20. All right, and then we're going to solve the equation. But this information helped us set up, know how that the distances should be set equal to each other. And we used the table to organize all of the information in the problem so we could have an expression for each distance. All right, so we're going to subtract 2.5t from both sides. And we're going to get 0.5t equals 20. Divide by a half. Okay, so 20 divided by a half equals 40. So that's helpful. Okay, but we have to take this amount and put it back in here to find our rates. So we know Ted, the rate, went 40 miles per hour. Okay, and then we know that Jeff, because he's Ted's rate plus 8, went 48 miles per hour. And there is our answer. So there are a lot of steps in each of these problems. I know that, okay? But it is imperative for you to know how you can organize the information, and then also imperative to know which formula you put it in, okay? How they should be set up. All right, so let's flip over to the back. We've got 2 more problems there to do. All right, so this first one, example 2.2. All right, we've got trail runners race up the trail at a rate of 4 miles per hour and down the trail at 5 miles per hour. If it took them 30 minutes less down trail, what was the total distance traveled? Okay, so let's look at what kind of problem do we have here. If they're racing up the trail at a rate of 4 miles per hour and down the trail at 5 miles per hour. If it took them 30 minutes less to go down trail, what's the total distance? So we're racing up the trail and then down the trail. What type of problem is this? What type of problem is this? Great, it's a round trip. Okay, so this is a round trip. So we know that our distances are going to be equal again, right? We're going to set our equal. And if you don't, you could write equal distances, or you could also write like D1 equals D2. That's actually shorter, right, than writing equal distances. So that's probably what I'll do in the future. All right, so let's find the key information here. The trail runners race up trail at a rate of 4 miles per hour. So this is them going up the trail. And down the trail at 5 miles per hour. Okay, so we're going down. So those are our things here. Like we're going to have up the trail and down the trail. Right? We don't have people, we just have up and down. And we know their rates. Up trail is 4 miles an hour, down trail is 5. Okay, if it took them 30 minutes less to go down trail, all right, so 30 minutes, I'm going to put my arrow down here, over here, to show that it's down trail. So 30 minutes less down trail, what was the total distance traveled? Okay, so we're looking for total distance traveled as well. Okay, so our time then is it took 30 minutes less. All right, well, time again is duration, okay? But we're not talking, we need to probably convert this to keep our numbers small, right? Time is always in hours. So let's convert this. You can write it as a half or 0.5, but it took 30 minutes less to go down trail. So we got to think, do I know how much time it took to go up trail? Nope, we sure don't. So we could put in the T there for time. But we do know it took 30 minutes less. So then for down trail, we would have T minus 1/2 or T minus 0.5. Again, whichever one you want. All right, now that we have our rate and our time, since we have our rate and our time, we can complete the distance. Because remember, this is just multiplying. Rate times time equals distance. So this is 4T. All right, rate times time is going to equal our distance. So again, you could leave it as 5 times the quantity, T minus 1/2, if you wanted. Or you could go ahead and do that out and be like, okay, well, this is 5T equals 5 minus, or 5 times 1/2 is negative 2.5. Oh, I put a minus sign, or an equal sign instead of a minus sign, pardon me. Minus 2.5. You can put either of those in there. All right, now that we have our distances, oh, my marker didn't change, bummer. I need to put those into this formula. I need to set those distances equal so I can solve. Okay, all right, so I'm going to say, well, 4T equals 5T minus 2.5. All right, so then if I subtract 5T from both sides, I'm going to get negative T, negative 1T, equals negative 2.5. I just have to divide by negative 1, right, at that point. And then I have T equals a positive 2.5. Sweet. So I can put that, plug that back into my chart. So to go up, well, it took 2.5 hours. All right, and then to go down, it's 2.5, our T, minus a half an hour, so it took 2 hours. Awesome. Okay. All right, so did we answer our question? Was being asked. Ooh, wait, the question says, what is the total distance? It didn't even ask us anything about time. So did we waste all of our efforts? No, we did not. Okay, we still had to know how far we traveled, or we still had to know the time in order to find our distance. So we didn't actually have to do this part because the question didn't ask us how long it took us to go up and down. It's asking for our total distance. So we still need our time. So how do we find the distance that we traveled? How would we find the distance that we traveled? Okay, well, our distance is 4 times t. Okay, well, here our t is 2.5. So if we do 4 times 2.5, that equals 10. And that would be miles, right, we traveled, right? Because we've got miles per hour. So to go up the trail, we traveled 10 miles. How many miles did we travel to come down the trail? All right, we should travel the same 10 miles. Okay, so up we went 10 miles, down was 10 miles. So what did we travel total? What's our total distance? 20 miles. So this is our real final answer. Okay, so this problem is a great example that, like, it's not always just going to be solving for the variable. Sometimes you have to take another extra step and solve for the distance and then the total distance. Okay, this is why organizing your information is so helpful. And this chart is tremendously helpful for you to use. All right, one more. Aren't you glad we're going to be working on these in class together? All right. Next up, example 2.3. Two airplanes leave at the same time from airports that are 880 miles apart and travel toward each other. If one plane travels 126 miles faster than the other and they pass each other in 2 hours, how fast is each plane traveling? Alrighty. So, first of all, what type of problem is this? Two airplanes leave at the same time from airports that are 880 miles apart, and they travel toward each other. Okay, so this should be motion in opposite directions. Good. Okay, so if we have opposite directions, what does that tell us? Okay, so that's where our distance is. So d1 plus d2 equals a different distance, like that total distance. So let me draw a picture. Maybe that would also help with this problem. Okay, so we've got two airplanes leave at the same time from airports that are 880 miles apart. So if I have an airport over here, okay, and I have an airport over here, and I have these two airplanes leaving at the same time, traveling towards each other. That one line got really long. But I also know that these two airports are, that total distance, okay, is 880 miles. That's what they said. They're 880 miles apart. And one airplane travels 126 miles per hour faster than the other, and they pass each other in 2 hours. Okay. So this looks like, if I put lines here, that looks a whole lot like that diagram for opposite directions from earlier. Okay. So for our two airplanes, we don't really have a name for each one. So you can put something in here, like, you could have left and right. It kind of just doesn't really matter on what you want. But what do we know to plug in this chart? What do we know to plug in this chart? Okay, so we've got this pass each other in 2 hours, maybe you're thinking about. So that's the time, right? They've been in flight for 2 hours. Awesome. So that is one thing that we know. How about our rate? We know that one plane travels 126 miles faster than the other. Well, we don't know the rate of the other plane. Okay, so that rate would be 1, or would just be x. Okay, and then one plane is 126 miles faster than the other. So maybe we want to describe this as the other plane and this one as the one plane. Do you get it? If one plane travels 126 miles faster than the other. Okay, hopefully you chuckled. Anyway, so then this plane, the one plane, is going to be the same rate as the other plane plus the 126 miles faster. Okay. All right, so now we're ready to get our distance. Remember, we just multiply our rate times our time to get our distance. So the distance for the other plane is going to be 2x, and the distance for our one plane is going to be 2 times the quantity, x plus 126. All right, now we're going to go back over here, and we recognize that we have to, our distance 1 plus our distance 2 is going to equal our n. Okay, so that new total distance. So we're going to add these two distances this time. Okay, so we're going to take 2x and add it to the quantity 2 times x plus 126. And that's going to equal that total distance. Remember, it equals this one, which we know is 880. Okay, so again, this is just that D1, let's see, D1 here, plus the D2 is equal to n. We're using that formula to set it up. And we got this, our D information, from our chart that we were able to pull it all together. All right, so now let's solve it. So we've got 2x plus 2x, because we're distributing, 2 times 126 equals 252 equals 880. So minus 252. And we're going to go ahead and add 2x plus 2x. So we've got 4x equals 628. We're going to divide by 4. And x is equal to 157. All right, so that's our x, which means our rate, the other plane, went 157 miles per hour. And our one plane went 157 miles per hour plus 126. All right, which is 283. And is that the question they asked? How fast is each plane traveling? Yes. So this time we didn't have to do all the extra problems. Woohoo! Okay, just those. All right, that is it for today, and using doing some motion problems. So hopefully you remember we did some of these as well in Algebra 1, but we're getting more complex using distances as well. All right, I'll see you tomorrow. Have a great night.